Okay, great.
Hey, Suvan! Oh, long time no see.
Okay, so let me do a quick recap from what we did last time. Okay, so last time, starting from the generating functional of correlation functions, or actually like the log of this generating functional, which by the way is a generating function of connected correlation functions. I didn't say last time, but for this talk here it doesn't matter. Okay, so starting from this, we performed a Legendre transformation. To the variable, which I called like phi bar of x, which is the expectation value of the operator phi of x, and it's just given by the derivative of this generating functional w with respect to the current. Okay, so then this gave us the so-called effective action. Which is usually denoted with gamma. And this effective action is nice because it gives us the ground state of the theory. The ground state of the theory is given by ground state is determined by the points in field space for which this derivative vanishes. So this already looks like a potential, but now this is still a general function of x, but for our applications we are interested only in constant configurations. So configurations with phi of x, so this field here is constant, and then we get the so-called effective potential. And the ground state is again given by by the minimum of this effective potential. So these are the stable ground states. Okay, and the final thing, and then we start with something new. So then we use the fact that this is the generating functional of 1pi correlators. So using this, we could show that we could derive this nice formula for the effective potential. So there's the sum. I write it and then I let you have a look at it because I'm standing in front of it. Okay, so this is kind of the master formula we derived last time. So it tells us that we can obtain this effective potential by taking these 1pi correlators, and I will show you in a minute how we can calculate them, for n number of particles. So these are correlation functions for n number of particles, and then we just sum over all n and then multiply it by this field, and this gives us the potential. So this is just a function of the coupling constants and things like this, because we set the outer momenta to 0, and then we multiply it by the field to the nth power, sum over n, and that gives us a potential. Okay, so now 0?
Over there, over there.
I don't know. Okay, I erased this already. Okay, and now we're gonna use this formula to work out what is usually called the Coleman-Weinberg potential. And I'll give you the reference here. It's actually, the paper is quite old, but still very readable. So if you're interested, you can also. I mean, this is in principle standard textbook material, but the paper is so well written that you can actually also just look into the original paper, which is not always the case. If you just look on Inspire, you're going to find it. So, and just to point out, this is not Steven Weinberg, the guy, you probably know this already, right? So he has the slight misfortune of having the same last name as a very famous other physicist. So people often get confused. Okay, so let's apply this formula now to phi-4 theory. So let's write down. Okay. Let me write this. Let's apply to phi-4 theory. So the Lagrangian is given by the usual story. There's a kinetic term, and again I'm using mostly minus metric. And then there's a potential. And I'll use a subscript here to make clear that it's a tree-level potential, like zero loop. Okay, so V0 of phi is, okay, we have a mass term, and we have a quartic coupling. And we've forbidden the phi cubed term by Z3 symmetry, phi cubed term. So requiring that there's a symmetry and phi goes to minus itself forbids a phi cubed term for simplicity. Okay, so now looking at this formula, so now we have to, in this theory, we have to calculate these 1pi correlators, right? So, so as I said last time, 1pi means that you cannot separate the diagram into two pieces by cutting one line. Okay, so, and now in this theory, there's always everything is at least quadratic in phi, right? So there's always an even number of outer particles. So let's start. So the first thing we can write down is like a 2-point correlator. And let me, it's a bit schematic. So there's like a line like this. I'll say a bit more about this in a second. And then we have a one loop correction like this, right? And then of course there are higher loop corrections, but I'll stay along with you. So the next 1pi function that we can write down using Feynman diagrams now is the 4-point function. So there's a vertex, and then the first correction to this diagram looks like this. Right, you've probably all seen this before. Okay, now going to higher order. So the next one would be gamma 6. And yes, but there's now no tree level contribution, right? So we just have the lowest contribution is 1 loop. And then it continues like this. Right? Actually, sorry, let me draw this here. So I wanted to separate this. So. Okay. So let me just separate this into like a tree level contribution, which I'll call gamma n0. So these are just these two diagrams here, and a one loop contribution, which are these contributions here. Okay, so now a quick reminder also of the Feynman rules, but I guess you all know this. But, so an internal propagator, if we have a propagator with the usual beta factor, then a vertex, each vertex comes with a factor minus I lambda. Yeah, and then we have to integrate over any loop momentum. P over 2 pi to the fourth. Okay, so so this here is the simplest. This is just, I mean, for this I'm just using, it's just a vertex. So let's start with this one. So gamma 4, 0, just minus I lambda. And now there's actually, turns out there's another factor of minus I that I need to include because of my definition of the generating functional. But I mean, you can check that this is the right factor at the moment because this gives the right tree level potential. So I mean, it's completely fixed. Okay, so this one is a bit more. So this is not actually a propagator because. So you can write, you probably also know this, you can write a propagator as like, you can think of a propagator as a series of mass insertions. So you have like nothing, and you have one mass insertion, two mass insertions, and so on and so forth. And then you can resum these mass insertions and you get this expression, right? But these diagrams are not 1pi. So what I'm interested in the 1pi piece, which is the one that I cannot cut by cutting one line into two pieces. So it's just this one. So it's just one mass insertion here. So I have to write 2, 0, and there's also minus I squared, and then there's a minus I, the global factor. So these are the two tree level contributions that I have. So this piece and this piece. Okay, this was easy. So now let's go to the one loop contribution. So these one loop diagrams, and you can actually already write down the general formula. So for the one loop diagrams, I have. So let me first write it down, and I will tell you. So there's a loop momentum integral, right? And now I have for each vertex, let me write it down again, explained. Okay, so if I look at this, so I'm now labeling so n is now the number of vertices. So n here is the number of vertices. So 2n is the number of outer particles. Each vertex consists of 2 outer particles, right? So so the lowest one is kind of for n equal 1 is one vertex. I have one vertex and one propagator, right? So one vertex, one propagator. Okay, and then it continues, right? So for 2 vertices, I have 2 vertices and 2 propagators. So I get the vertex propagator squared, and so on and so forth, right? So this is how I can build up. I can build up all these diagrams to arbitrary number of outer particles. This is loop correction. This is not. Yes. Okay, and then there is a combinatorial factor that you have to work out by looking at the number of contractions, essentially related to the symmetry factor that you have. It's like an overall factor that you get that tells you how many diagrams there are and which contribute. So this essentially compensates. Well, I'll tell you. So, okay. So, that any questions so far?
How do you come up with that number?
With this prefactor? Yeah. Yeah. So this is essentially like the number of 2n is the number of ways you can connect with these vertices. So you have 4 outer particles, and so it's a combinatorial factor from how you can connect with the vertices. So 2n factorial different ways. And then the 2 to the n comes because, like, if you exchange these 2 or these 2, it doesn't give a new contribution. And the 2n is like also a symmetry factor that you rotate the diagram, it doesn't give a new contribution. So yes.
So about the first expression, why do you have these n squared? Why do you have these n squared in the first expression?
So I think of this as I think of the mass as a vertex here.
Okay.
Right? So I think of the mass as a vertex, and yeah, because I'm looking at 1pi diagrams, I need a diagram with only one mass insertion, because I mean the point was just to show that this is not a propagator. I mean, because you can think of a propagator as like a series of mass insertions, but we want the 1pi contribution, which is just one mass insertion. So okay, let's just put this together now, and you will see that it gives the right result. Okay, so we have this formula. Now we just plug it into here, right? And for simplicity, let me just drop the bar into C, so I just write it as phi now to make it less cumbersome. Okay, so now we have the effective of phi is equal to. So we have the 2 tree level contributions. Let me use them first. Did I do it correctly? Yes, so I have. So it always goes like 1 over n factorial. So I have 1 over. Okay, let me first write it like this. So 1 over. Let's do it slowly. 2 factorial phi squared plus 1 over 4 factorial phi to the 4th. So these are the tree level contributions, right? I'm just plugging this into the formula. And now we get a whole tower of 1 loop contributions. So let me just write this. So now I'm labeling n is again the number of vertices. So I have to write each vertex comes with 2 outer particles. So I now have a 1 over 2n factorial in the denominator. Right, so I'm replacing n here by n over 2, right? So I have 1 over 2n factorial here, phi to the 2n, and then gamma 2n. Okay? Okay, so now you see this here just gives, and there's an overall minus sign, sorry, I forgot, because of this, it's an overall minus sign here, right? So let me include this minus sign. Okay, now you see that this is just 1 over 2 factorial is just 1 over 2. This gives a minus sign, so I just get 1/2 m squared phi squared from this piece. And there's the same story. This gives a minus sign, and the minus sign gives plus. So I get plus 1 over 4 factorial lambda pi to the 4th. Okay, so this piece just reconstructs the tree level potential here, right? So far so good. Okay, but now the interesting piece is this one loop correction here. So the one loop correction now gives me also. So now I have to be a bit careful. So I get, okay, so the minus I and the I here compensate. Then I have a minus I here and a minus sign here, so there should be overall effect of I. Go on to infinity. There's a 1 over 2n factorial, which just cancels this one here. So I can write 1 over 2 to the n, 2n. There's a phi to the 2n again, and then this propagator here. So it's lambda over p squared. Okay.
Integrated over the first.
Yes, very important. Okay, is that clear? I mean, it's just basic math now that I'm doing. Okay, so now next, let's write this. It's a bit more convenient to write this as, so I can pull the 2 to the n in here. Sorry, what? Wait a second. I'm a bit. Just 1 second. Sorry, this is just to the n. So yes, exactly. So now I can pull this factor 2 to the n in here, so I can just get rid of it here, and then it just gives me this. A bit more convenient. Okay, another trick is to I can actually evaluate the sum in closed form and what it gives me. So let me write this like this, because so this was what we call V0 of phi, right? This is just a tree level potential that we know, we don't have to care about anymore. And this is, let me call it V1 of phi. That's the one loop contribution that we want to calculate now. Okay. So let me go here. Okay, and so the point is now that I can evaluate the sum in closed form, and what I get, and you can easily check at home with Mathematica or any other tool. I find that evaluating the sum, I find that this is minus I over 2 Yeah, what I've also done here is, so actually I can also do this here already. I can pull this in here, right, and I can write this as this. So I write it like this, then I evaluate the sum, and then the sum just gives me a log here of the argument. So yeah, I don't know if you can read it, but it's lambda over 2 phi squared over the propagator, the log of minus 1 minus this, and I have to integrate over d4p still. Okay, so next thing is that, okay, next we will perform a Wick rotation. So Wick rotation, just to remind you, if I am in the complex plane for the energy, then the Feynman, this plus I epsilon prescription gives me poles like slightly shifted by epsilon away from the real axis. So normally I would integrate, the integral over P0 would be like along the real line. But because the contribution of the integral like at infinity vanishes, I can just, so this is, so this. So this is kind of like the normal integration direction, but I can rotate it and integrate along the complex direction. So Wick rotation. So Wick rotation means I replace P naught, the zeroth component of the momentum vector, by I times something that I call P naught E for Euclidean, and PE is equal to minus P naught so that I can define this 4 vector PE, and then I can check that now P squared, so P naught squared minus P squared is equal to minus squared. All right, that's a little story. So let me just make some space here. Okay, so we have to work through this loop integral. Okay, if I, after performing a Wick rotation, what I get is Phi1 of phi. I get a plus 1/2 because an overall factor of P of I coming from the Wick rotation. Now I integrate over the Euclidean momentum, and I have this expression. And now I can drop the plus I epsilon, because this was just to remind us of where the poles are, right? Because now we are completely avoiding the poles, so we don't have to worry about it anymore. Okay, is that? I guess you've all seen this before. So, okay. So next step is I have to go through a few steps. Now let me define a field-dependent mass. So I introduce this object m squared of phi, which is equal to, it's just the second derivative of the tree-level potential with respect to my field phi. So this is kind of the mass of the field if phi has a vacuum expectation value. And yeah, I can just write it like this. So m squared of phi is the mass of the field if phi has a non-zero non-zero expectation value. Yeah, and I hope it's not too confusing, so you always remember if it's an argument of phi, then it's this expression. If none, then it's just independent mass. Okay, so now I can write this as p e squared plus m squared plus this. I just extend this, right? And now this expression here, you see, is exactly this field-dependent mass. So I can rewrite this as, let's do this, as this field-dependent mass. And now, so I can write the log as like log of this minus log of this. But log of this, like this does not depend on the field, so it just gives a constant contribution to our potential. A formally divergent contribution, but yeah, it's just a field-independent contribution which we can deal with separately. I mean, in the end, we'll have to also renormalize the cosmological constant, but we don't have to worry about this here, so we can just drop this piece. So this is what I get. Okay. Any questions so far, or no?
So the integral. No, so you didn't do the integral yet. Okay.
I didn't do the integral yet, exactly. So for now, I didn't do. I just rewrote things. Like I summed and I Vic rotated, and now I dropped this constant piece and I introduced this field-dependent mass. So this is the expression that I have now. Okay, but now we will have to integrate. And this integral is UV divergent, so we will have to regulate. And the way I will regulate this integral is by dimensional regularization. So regulate this dimensional regularization, Dirac. And the idea is simply to go to analytically continue from an integral over d equal 4 dimensions to d equal 4 minus some small correction term, which I parameterize by some number minus 2 epsilon, and epsilon is small and will be sent to 0 in the end. I guess yeah. Okay, so if I do this, so now I'm replacing essentially wherever d equal 4 appears, so here, and this is also coming from the fact that we are living in 4 dimension, there's 2 pi to the 4, I replace it by d equal 4 minus 2 epsilon. But for now I just label it with d, so I get v1 of phi equal to 1/2. And now, so I write this d to the d, p, 2 pi to the d. And now, because d is no longer 4, but we want to keep the potential in 4 dimensions, we have to introduce some compensating mass scale that I will denote with mu. So it's just some mass scale that is not specified at this moment, that we just need to introduce for dimensional reasons. Okay, and I still have this factor. Let me just check how are we with the time. No, it's okay. It's okay. Okay, so next step is, now we'll use a trick. I will not actually calculate this object. I will take the derivative with respect to this field-dependent mass. And then I will integrate. So what I actually, so here's the trick. We will first calculate d1 of phi with respect to the derivative of this potential with respect to the field-dependent mass. And then we integrate again. And so what I could miss, if I do this, what I could miss is some constant that is independent of m squared of phi. But again, that's just a contribution to the cosmological constant that we don't worry about here. We are only interested in phi-dependent terms, so it should be a safe procedure. Okay, and now we're using like kind of the master formula of dimensional regularization. So the formula is okay, I'll write it down and then I'll explain it. I'll say what is notable about it. Okay, so it's just a general formula, like whenever I have an integral of this type, with some coefficients alpha and beta, that's what I get if I evaluate the integral. So it's just, you can find it in all the textbooks. And yeah, so I don't know if that's readable, so this is a gamma function of alpha, so this is a gamma function, all right? So of alpha plus d over 2, beta minus alpha minus d over 2, here is this gamma of d over 2 and gamma of beta. Okay, now let's apply this. So I'm taking the derivative of this. So d1 of phi, dm squared of phi is equal to 1/2. Nothing happens with this. Still have the integral. And I get a 1 over I should here I forgot I labeled subscript E for dB momentum. Okay, so I take the derivative, that's what I get. And now I can just apply this formula. And what I find just write it down, you can check it yourself. I mean, it's very straightforward. So I get d minus, sorry, what is this? Okay, so I'm using this formula for alpha 0 and beta 1. Okay, now you just evaluate the right hand side. This capital M squared is now m squared of phi. Okay, and this is what I get. hurry a bit. Okay, now I integrate this. I take this expression and integrate again over m squared of phi. So this essentially gives me like 1 over d over 2 here, and then instead of minus 1, it's just d over 2. Okay, so I get to the minus d. Sorry, where am I? To the d, 1 to the d over 2. That's 1 over d over 2 from integrating. I still have this compensating mass scale here. I get m squared of phi to the d over 2. And I get this gamma function of 1 minus d over 2. Okay? Okay, so now we're almost there. So now what I do is I just replace, so again I set d to 4 minus 2 epsilon with the idea of taking epsilon to 0 in the end, right? To go back to our 4 dimensions that we know and love. Okay, and I think I'll just write down the result now. You can, if you want, you can try this at home. I mean, you can plug it into Mathematica essentially. You just replace d by 4 minus 2 epsilon, and then expand in epsilon. And then what you will get is this expression. 1 over 64 pi squared, n to the 4th of phi. So 1 minus okay. So now this already looks a lot simpler than what we had in the intermediate steps. So this is the so-called, this is the Euler-Mascheroni constant. And what is to note here is that I have this 1 over epsilon pole, right? So, and now if I take epsilon to 0, this blows up. So I have to renormalize this theory. Okay. Let me erase this. I should hurry a bit. So I need to renormalize this theory. And so what you do to renormalize and so-called renormalized perturbation theory is you just essentially shift the parameters in your potential to in your Lagrangian by some counter terms. Okay, so I just rewrite the coefficients of my terms in the Lagrangian in terms of some renormalized quantities and some counter terms. And then you just adjust the counter terms in a way to absorb this infinity. Okay, so let's say, so these are the counter terms. And this one, but this one here we don't need because we are dealing with a theory at zero momenta, right? So there's no kinetic term renormalization in this example. Okay, anyway, so what we will do now is we'll use this so-called MS bar renormalization scheme. And this just consists of like throwing away all terms in the potential which are proportional to the following constant. So the idea is these counter terms give me new vertices, so I get kind of new contributions to the one-loop corrector potential. Yeah, and then I just adjust the counter terms in a way so this is this piece, right? To cancel off this constant times this piece. And yeah, I think I'll skip this step. You can check at home if you want to. It's straightforward, so you can just find. So use this as a new vertex, and then you just adjust this counter term delta m squared and delta lambda in a way to cancel off this piece. So this is not a very often if you renormalize, you can relate to physical parameters like, I don't know, the pole mass or things like this. Here we have to do kind of another step. So this is, at the moment, we are just dropping the divergent piece, and it's not yet clear how the parameters in our potential are related to like things that we can measure. So this is kind of another step that you have to do. But yeah, it's a valid renormalization scheme. So all we have to do in the end is really just getting rid of the divergent piece.
Is there a reason why you want to keep the minus 3/2?
The minus what?
The minus 3/2, you want to keep it apparently. Why?
Yeah, not sure. So this is kind of, well, I guess, no. So because, I mean, essentially, you will see in a minute that you get different constants for different contributions. So I will show you in a second that for fermions and for fermions you get the same, but for gauge bosons you get a different constant here. So I guess it's convention. I don't think there's any deeper meaning to it. So, right, or do you know, is there any? Yeah, the only reason I see is that if you work this one-loop corrector potential out for gauge bosons, you actually see there's a factor 5/6 here. So that, of course, you could say that you want to cancel this off for. Yeah, I'm not sure. Okay, so doing this, what we get is log of m squared power 5 divided by this constant mass scale. Well, I should probably write like this because in this step I've renormalized. Okay, so we are there. This is the formula I promised to you in the beginning, like going through a lot of painful steps, defining the effective potential, and now calculating this loop integral and evaluating it and renormalizing, and that's kind of what we get. And it turns out that this is actually more universal. So you can show that, like, I mean, whenever you have a theory that depends on a scalar theory, that depends on, well, if you have a complicated scalar potential, right? I mean, you can always replace, you can get the one-loop correction to the effective potential, to the potential, by just using here for m squared of phi the second derivative of the potential in respect to the field. So it's a more universal formula. I've derived it in one special case for phi-4 theory, but it applies more broadly. So in the end, what you have to do, you just have to remember this formula. So if you have a formula, if you have a potential, so some potential via phi, which is not necessarily of the form that we assumed, then you just have to use in this formula like the second derivative of this potential with respect to the field. Okay. Okay, any questions? Or this would be a good, yes?
I got to know, isn't it just 1 over epsilon, the divergent term?
Exactly, but I mean, it's just a choice. I can also subtract constant pieces. Okay. So, exactly. So it's just convenient to also subtract the other. I mean, essentially shift my counter terms by a finite contribution, which gets rid of these constant contributions. So
Yeah, that's the definition of MS bar.
exactly. That's just a definition of MS bar. So you always just subtract like this contribution, like which is proportional to these three terms.
Okay, thank you very much.
The m squared, it's a definition that m squared is the second derivative of potential.
Well, I mean, this is how you would naturally define, like if you have a field in some potential, yeah, that's how you would naturally define the mass, I mean, away from the minimum. So yeah, if you want, it's kind of definition for the mass of the field away from the minimum. But I mean, it also applies in the minimum, right? So it's, I mean, it kind of also it applies to like regions in field space where you don't actually have a physical mass, right? So if you have, I don't know, you have such a potential, right? So what you would normally call the mass is kind of if you're down here in the minimum, right? That's kind of the mass. But this is completely generic, so you can also evaluate it here or here, I mean, wherever you want. I mean, you just take the second derivative and plug it into this formula, and that's all the correction. Yes?
So in this whole process, you added a new parameter, which is this mu, which you use to expand the dimensions. How do you determine this parameter?
So this is kind of well, we will see in a moment what it is really. I mean, but well, I can tell you it's what is called the randomization scale. So it's kind of, I mean, it's the same mu that you see like if you calculate running couplings, for example. It's kind of the scale at which you define your coupling, and then yeah, if you change the scale, then you have to run the coupling from your original scale to the new scale. Right? So with the RG equations, and actually we'll see this in a second. So because now let me just check. I have to hurry up because I wanted to. No, it's okay. Any other questions or? Okay, so now you can easily generalize this, and I will not go to other fields. So for example, if I have a U1 gauge field coupled to some complex scalar, so right now it's this. The kinetic term from the gauge field. and I have a kinetic term for the complex scalar phi, and d mu is just a covariant derivative. And yeah, if phi now gets a vacuum expectation value, the gauge symmetry is broken, and the U1 gauge field gets a mass, and the mass as a function of the vacuum expectation value of the field is given by this expression. So 2g is the gauge coupling, 2g squared, phi squared. So you see, this essentially is just a field-dependent mass, right? So what enters in this formula is really like the field-dependent mass. And I can do the same game now with the gauge field. So now I have a gauge field that that kind of gives a contribution. So now the quantum fluctuation of this gauge field give a contribution to the effective potential of the scalar phi. And the way I can calculate this is, again, with this field-dependent mass. And the formula looks very similar to what we had before. So let me read this. So this is what I get. So again, I calculate, so the stretch is always, I calculate a field-dependent mass of the field with quantum fluctuations I take into account, and then I plug it into this formula. Now for the gauge field, the formula looks almost the same, except that I have an overall factor 3 here, and the factor 3 is just because I have, for a massive gauge field, I have 3 degrees of freedom. Yeah, and then there's this other concept here that I was already mentioned before this. Instead of a minus 3/2, there's a minus 5/6 that pops out. There was a question?
Is G the new coupling?
No, G is a gauge coupling here, right? So G is so I have the kinetic term here. Yeah, if you haven't seen this before, this is kind of like spontaneous symmetry breaking. So the way I couple a complex scalar to some U1 gauge field is by replacing the derivative by the so-called covariant derivative, where I have this extra piece plus I gauge coupling times the gauge field. And now you see that if you can work it out, right? So if phi now has a background value, so if phi has some vacuum expectation value, then this gives rise to, so there are mixed terms, but then there's a phi squared a mu squared term. So I get essentially g squared a mu squared phi squared from this, right? So just this piece squared times this squared. And now if phi has a non-zero background value, then this is a mass term. So, and this is essentially the Higgs mechanism. So this is how like in the standard model, if the Higgs get a vacuum expectation value, then like some gauge bosons get a mass. So this is, yeah, sorry if you haven't seen this before. So it's yeah, but anyway, so yeah, then you see that kind of, so you have this field-dependent mass. There's a factor 2 here because I should write it as like this overall factor of 1/2. So I have this field-dependent mass, and then I plug it in here. So this is essentially, I'm kind of taking into account now contributions like this, for example. So I have, so now I think of it as my 1PI diagrams. I have 1PI diagrams where there's kind of the gauge field running in the loop, and this gives a correction to the scalar potential again. So, any other question?
How do you deal with the Gauss
Yeah, very good question. So this is a Landau gauge, and in Landau gauge you don't have to worry about the ghosts. I mean, so now I forgot. Well, I mean, one question you could ask: can I have kind of mixed diagrams, right? So I could have. One second. How did this go? Yeah, I think, okay, I'm not 100% sure about the details, but I think the point is that kind of the ghost, so you can have contributions with ghosts running here, but this contribution cancels or is zero. I mean, this is kind of.
In the Feynman gauge,
yeah, and what
they all are the same mass, so it's easier to make calculation.
So okay, so it's definitely simple to calculate in Landau gauge because I think you don't have to worry about like mixed diagrams when you have like this. With a ghost, I guess. I don't remember exactly how it works. So the point is also, I mean, something to note is that the effective potential is actually not gauge invariant. I mean, this is kind of like this is something that causes a lot of discussions in the literature. So the exact form of the effective potential is not gauge invariant. One can show in some cases though that, for example, I mean, what I really care about, if I have like effective potential like this, what I mean, the physical quantities are things like this wave here, right? Maybe the energy difference and the tunneling rate. And I think you can show, at least in some cases, that these quantities are gauge invariant. But I mean, the exact form of the potential is generically not. So this is also something to keep in mind. I mean, it causes a lot of discussions in the literature. I mean, and confusion. So it's not a completely settled subject. Yes. Yeah.
The m square of phi, you define it as m squared per n squared plus a term proportional to lambda.
So this was for the 5-4 theory, right? So for the 5-4 theory, but now my point was that this formula applies more generally. So even if I have a more generic potential.
No, let's talk about this 5-4 theory.
Yes.
If I consider lambda equals to 0, this potential will not hit 0. But when lambda is 0, we are at the infinity.
Yeah, it will give some constant contribution to, which again, we don't care about. I mean, we've thrown away constant contributions all the time. So exactly. So if lambda is 0, your point is that I get a constant, right? So, but that's just a contribution to the cosmological constant that we don't that we're not keeping track of, so to say. Okay. Anything else? Okay, let me just, for completeness, although we will not need it, just quickly say, so for a fermion, you can do the same thing. So let me, I should hurry a bit. Okay, so for fermion, you can do the same thing. Okay, so the Lagrangian now, let's say it's given by this. And the kinetic term for the fermion doesn't really matter, and I have Yukawa coupling to some scalar phi. And now again I can define like a field-dependent mass. So well, let's square it because we're always squaring it. M squared of phi is just Picard coupling squared times phi squared, right? So again, I have a dependent mass, and there's a Coleman-Weinberg formula that tells me now, essentially integrating out the fermion, the loop corrections from the fermion, what is the contribution to the effective potential of my scalar phi. And again, it has a very similar form to what we had before. So now the difference is, okay, I have an overall factor of 4 because the Dirac fermion has 4 degrees of freedom compared to the scalar case. And there's a minus sign, which essentially I think comes from the fermion loop. Fermion loops always come with a minus sign. So now I'm integrating out. Well, I cannot really draw it because so I'm integrating out things where now this is the fermion, right? And so I'm using the same type of lines for fermions and scalars, so it's difficult to draw. So the outer particles are scalars, and the particle running in the loop is a fermion. Diagrams like this. Yes, so there's overall factor 4, there's a minus sign from the fermion loop, and this term is the same. Anyway, so the point is kind of then these like universal formulas that you can now just bluntly apply. I mean, you can forget about all the derivation, all the pain we had to suffer to get there, and you just can use these formulas to calculate the one loop correction to the potential of some scalar field by using these field then.
You don't have quartic couplings between fermions and scalars, so that's probably the diagram.
Ah, sorry, this is bullshit. Yeah. Sorry. You're right. Sorry. What do you have? So you have. Yeah. Sorry. You're right. It's like this. Yeah. Sorry. So then you have this, right? Yeah. Sorry. Okay. Okay. So now let's put this to use.
Sorry, just one quick question. I don't remember. For some combination of fermion, scalar, and vector, is there a cancellation? Like a supersymmetric, when you have a supersymmetric combination?
I guess yes. Yeah. Of course, exactly. You should be able to see, for example, in the supersymmetric theory, if you add up the contributions of the superpartners, fermions and scalars, you should cancel it. So.
Yeah, so like if you look at this fermion here.
Yeah, I'm not sure. Well, this fermions and scalars is easy, right? Because now this comes with a minus sign.
Yeah.
Right? I think that's just that. So you have the same mass. You have to have the same number of degrees of freedom.
Yeah. So for the scalar, it was.
For the scalar, it was, so there's a plus sign, and it's 1 over 4.
4, yeah.
But this is the same, so.
Yeah.
So I guess.
That's a Dirac fermion.
That's a Dirac fermion, so you probably need, you need the same number of degrees of freedom, right? You need 4 scalars. So then the potential should exactly cancel. It's actually a nice way to see that you need a minus sign here. So exactly. Okay, let me hurry a bit because I'm not actually get to. How much time do I still have? Okay, I think I can still do it. Okay, so now let's apply this to the so-called Coleman-Weinberg model. And what we'll call here the Coleman-Weinberg model is scalar QED. So, yeah, a U1 gauge field coupled to a scalar for a massless scalar. So But further, there are other theories, like where you also have this effect, which are also often called common Weinberg model. But the original one was, I think, this one. So let's discuss this. So I have a U1 gauge field. And then we have the kinetic term. And I have the quartic coupling for my scalar. So note that, yeah, as I wrote already here, I assume that there is no mass term in the theory, and this will be important. And now those of you who have heard about the hierarchy problem can now start to worry if this is natural or not. Yeah, in principle in this theory there's no other mass scale, so some people say actually you don't have to worry about the hierarchy problem in the theory. Although then you couple it to gravity, which has another mass scale, so maybe you should worry. Anyway, this doesn't matter for us. I mean, depending on your taste, you can either think of it as a full model or just as a toy model where I just tune to get the mass term to zero. Okay. So this theory has at the classical level, so just this Lagrangian, at the classical level has the action is scale invariant. It has a symmetry that so invariant under scale transformations, and I will show you in a second what this means. So this means if I rescale the scales in my theory, then the theory is invariant. So the way you can see this is, so first of all, if I rescale my coordinates by some constant lambda, so this is one scale. I'm changing kind of the length scale in my theory. But now the fields have mass dimension, right? So I should now, to be consistent, I should also rescale the fields. And they should be rescaled inversely proportional with this constant. So okay, so I rescale I rescale the length scale in my theory, and I also rescale the fields with the inverse rescaling factor lambda because they have mass dimension to be consistent. Okay, and then you can easily work out. So F mu squared is so there's a d to the dx, so it gives me a 1 over lambda, and this also gives me a 1 over lambda. And then I square it, so overall it goes like lambda to the 4 F mu squared under this rescaling. Same for the kinetic term. So d mu 5 squared is equal to the covariant derivative. So again, this gets like 1 over lambda, this gets like 1 over lambda, this gets like 1 over lambda squared, this gets like lambda to the 4th. Yeah, and the final thing is we have, in the potential, we have this term. And it gets again like this. And now the action, the statement was about the action, which is really the object that matters here. So the action is the Lagrangian density integrated over d4x. So the Lagrangian density, as I just showed you, it scales like lambda to the minus 4. d4x scales with lambda to the 4, so it's invariant. So the action is invariant. And you see it's important that I don't have a mass term, right? Because if I had a mass term, then this scalar invariance would be broken by this mass term. So now the question is, does this survive at the quantum level? And as you can maybe guess, the answer will be no. Let me show you. Okay, so preserved at quantum level. Okay, so in order to answer this question now, let's work out the effective potential. So I will expand my scalar field around some vacuum expectation value, some background value, and I will introduce two scalar fields, chi1 and chi2, which are real and which are just kind of fluctuations around this. Phi is a complex field, right? So I need two real degrees of freedom to account for the possible fluctuations around this field. So now I can work out the mass of these guys in this background. So just from, right, I have my potential now is given by so now I just plug this expression in here and extract the pieces that go like chi1 squared or chi2 squared. Those are the masses of these two guys in a constant background phi c. So I can write it as, I can rewrite the potential instead of phi, I can write it in terms of chi1, chi2 now. And now I can write this out. And same for this other guy. So I don't repeat this. So now the second derivative with respect to chi2, and this is given by lambda over 6 phi c squared. And the last mass I need, so if, as we said before, if phi gets a vacuum expectation value, the U1 gauge symmetry is broken and the photon gets a mass, or the U1 gauge shield gets a mass, right? And this mass is given by, this is what I had on the blackboard before. Where?
No.
Yes, it's phi c squared, sorry, yes. Exactly. I mean, for dimensional reasons already, right? So this is kind of... Okay, now I just work out the effective potential. So I'm just using the master formula that we derived. And I'm interested in the effective potential as a function of this background field, right? I mean, so this is kind of the field that gives masses to particles now, and those potential will be corrected. Okay, so then I just have the tree level contribution. So this is just this piece if I just keep this term here. And now I have 3 one-loop corrections. I don't know if that's readable what I'm doing here. So I'm just adding now, I'm plugging these masses, these field-dependent masses into the formula, to the master formula, and I get three one-loop contributions from the two scalars and one from the gauge boson. Okay, so I use the master formula, use these three states here, and that's what I get. Okay, so now for simplicity, let's go to regime, and then later you can check that this is kind of self-consistent. Let's go to a regime where lambda squared, that's the quartic coupling in the scalar potential, is much smaller than the force power of the gauge coupling. And now you can see that so these masses go with lambda, and this mass goes with g squared. So these terms go with lambda squared, and g to the fourth. The reason for this assumption is just I want to get rid of these two contributions. So these are now, I go to a regime where these two contributions are small, and kind of the relevant correction to the potential of the scalar field arises from the U1 H field. Okay, if I can just, so let me, okay, so now I drop these contributions and the potential simplifies a lot. Okay, so I keep this term, I throw away these terms, I keep this term, I use the expression for MA as a function of phi c, it's 2 MA squared is 2g squared phi c squared, so I plug this in here, that's what I get in this limit. So now let's simplify this expression a bit by defining, so let's define a mu scale mu tilde equal to e to the 5, 6. That's to get rid of this ugly constant there. Mu squared. Sorry, what am I doing? Yeah, like this. I guess I have to do mu squared. So I'll just, out of convenience, I redefine this scale here. That for now we haven't really specified what it is. I can just redefine it in this way, because then what I get, something that looks slightly more simple. Okay. So I have so again, the effective potential is just the tree level potential plus some correction term that goes like phi to the fourth, but now proportional to the log of phi. Okay, so now we can now we're almost there. Now we can let's define an effective quartic coupling. So let's just define this quantity lambda plus okay. And if I introduce this quantity, then I can rewrite my effective potential just in a very simple way. As this effective quartic coupling, which now is a function of this field, phi c to the 4th. Okay. So I've kind of, what the one loop correction does is it replaces, effectively it replaces the quartic coupling lambda in the tree level potential by an effective quartic coupling which depends on the field logarithmically, right? So it's just lambda plus this logarithmic correction. And those of you who have seen, who've seen running gauge couplings before or running couplings, I mean, this is exactly the same phenomenon. So in a particle physics experiment, like if I have a scattering process, then kind of the best point to evaluate my gauge the couplings like that are involved, that enter the scattering process, is kind of the energy scale of the scattering process, right? So kind of if I have the couplings at some other scale, I have to run them to this energy scale. And here you see something very similar happens. So here, kind of what I should use in the effective potential is not kind of the tree level quartic coupling, but I have to kind of RG evolve it, run it to a different scale. And this scale is given by the VEF. This is how you can think about this. Okay, let's put this to use. So now let me just plot. Yeah, and in particular you see now, exactly, so now you see, kind of you get a better idea of what the scale is. The scale mu tilde that I've now introduced, if I evaluate this coupling at the scale mu tilde, I get lambda. So mu tilde is kind of, yeah, again like in the other example I said, it's like the RG scale where I define my coupling. So lambda effective of mu tilde is equal to lambda, right? So if I set phi c to mu tilde, this log is 0, and I just get lambda. So this is really kind of the physical meaning of this scale mu, or if we find it mu tilde, that enters after I use DIMREG. It's kind of like the RG scale where I define the coupling. Okay, so let's now plot this. So let's assume this coupling is negative. So this is kind of like the coupling that enters the lambda, the coupling that enters the tree level potential, and which is the effective coupling evaluated mu tilde, is negative. So now let's plot this. So now I plot this coupling as a function of the background field, phi c. And so as I said, right, so at mu tilde, we know that lambda is negative, so and the negative value is given by the, I actually should write like this, right? Given by the absolute minus the absolute value of lambda, so the coupling is kind of here, right? Now if I increase phi c, then this log becomes larger than 1. This is all positive, so the coupling grows. And eventually it will grow and become positive. And then if I go in the other direction, it becomes negative, right? So, okay, so what does it mean now? So, yeah, this is this effective coupling that enters into the effective potential. So what does it mean now for this potential? So let's draw the potential. Where do I do this? Here. So now I'm drawing the effective potential. Of phi c. Okay, so again, phi c effective potential is just lambda effective over whole faculty phi c to the 4. So we see that like the point where it crosses 0, just one second. The point where it crosses 0, the potential must vanish. Right? So we are here. Then also if I send phi to 0, the potential also vanishes. So I know that I'm here, and I know that I'm kind of at the origin. I'm also at 0. And then we also know that the quasi-coupling is initially negative. So what it means is really I'm first going down. The coupling is negative, right? The effective becomes smaller, and then I know I have to cross it, so it has to grow again. And now what do we have? Sorry?
Because of the effective lambda, we can see that if phi c is 0, then the effective lambda goes to, right?
Sorry?
As phi c goes to 0, the log goes to minus infinity.
Exactly. So the log diverges. Exactly. Exactly. So this is why I draw it like this, right? So if you send phi c to 0, this log diverges. Exactly.
So the vacuum is shifted from 0.
No, because then you multiply this by phi to the 4th. So if you have something, so the log diverges, but phi to the 4th goes to 0 quicker, right? So that's why you're still at 0 here. There's actually something I completely glossed over, that like in this regime your perturbation theory actually breaks down, and you have to do something that is called RG improvement, because the logarithm blows up. But the effect, if you do that, if you do it, be careful, then the effect is still the same. So in the regime, you can check that kind of like in the regime where in the minimum of this potential and beyond, perturbation theory is fine. So that's kind of what so anyway, so that was kind of the big point. I want to emphasize it again. So we started off with so essentially like at tree level, I can also draw it at tree level now. So V0 of phi is just lambda like this, right? And I said lambda is negative. So at tree level, the potential just looks like this. It doesn't have a minimum, right? Just keeps going down. And now what the quantum corrections do, they correct the coupling that enters here and correct it in a way that the coupling turns from being negative to being positive. So this is why I first go down because the coupling is negative, and then I go up again. So quantum corrections have generated like a minimum in my potential. This is there's the upshot. This is kind of the big point. What they also do is, and what you can also check now, is that it's no longer scalar invariant. So if you do this rescaling now, essentially because you have this scale mu here that you can check that scalar invariance is broken. And yes. Okay. So anyway, this was kind of what I wanted to. I think now it's a good time to stop. This is what I wanted to do today. Sorry, I went a bit over. Okay, so this is kind of, I mean, I just, as I said, so I discussed this kind of because, well, because I wanted to derive these general formulas for the one-loop correction, because they are like relatively straightforward to generalize to the non-zero temperature case, which I will do next time. And then next time, or maybe the time afterward, the lecture afterwards, I want to discuss the cosmology of this model, of this co-environment model, because there's some very interesting aspects. That's another reason why I kind of derived this this potential in this case. So keep this in mind. We'll hear later. Okay.
More questions for Benedict?
No.
Because there were many questions during the lecture.
Exhausting.
Okay.
Anyway, just also if you have, feel free to come to my office. Right? I think.
And his office is on the first floor.
Yeah,
102.
102, exactly.
Just in front of the elevator.
Yeah, I'm happy to chat. Yeah, next time the plan is to do the thermal corrections, and then hopefully at some point this week I will get to the cosmology of this model, and we'll finally talk about cosmology.
And if you haven't written our name here, please do. Thank you again.
Actually, I'm working with this model.
Ah, okay.
We must do the
Ah, okay.
and to know that